Hi, my name is Abraham Kim, and I was mentored by Dr. Wu, and I will be presenting on behalf of this research team for this paper called User-Centered Evaluation of a Visual Annotation Tool for the Rapid Assessment of Pediatric Weight Entry Errors. Here's the disclosure statement saying that we have no relevant relationships with commercial interests to discuss. After participating in the session, one should be able to understand the clinical significance of pediatric weight entry errors and the consequences they have on patient safety. One should also understand the purpose for the development of the visual annotation tool and understand from our methods how to conduct usability testing. So in the field of pediatrics, collecting weight data from patients is absolutely critical because weight is a large factor determining medication dose. You can see why perhaps an error in weight entries into electronic health records might have a significant impact on the patient. So as we talked about, if you have an incorrect weight data entry, this can negatively impact medication dosing, which in some cases may be life-threatening and fatal. One statistic states that a large percentage of pediatric medication errors was simply due to the, incorrect medication dosing. And since when weight entries have a significant impact on pediatric medications, you can see why this might be a significant issue. So how do we fix these errors? Well, we can do them manually. That is always, of course, an option. However, considering that there are millions of weight entries and hundreds of thousands of growth charts, if we begin to think about how much time is available for medical experts, it's really not a lot for this size of a data set. So there needs to be a more efficient way of going through these, which leads me to my next point. That is, what if there was an algorithm that could go through the charts and detect the errors for the clinicians to review? So previously, we have analyzed the current methods out there in a past study that we conducted, which includes some methods from Children's Hospital of Philadelphia, the CDC, and our own regression model developed in a previous study, which can be found in the following PubMed ID. We have found that current methods do not have outstanding accuracy, sensitivity, and detection for weight entries with high clinical significance. Therefore, there's definitely room for improvement for all of these algorithms. So we've talked about the comparisons of existing models. Because we need to improve these algorithms in the categories mentioned in the previous slide, we find it absolutely necessary to make the algorithm a supervised learning process. In other words, trying to have the algorithm imitate clinicians as realistically as possible when detecting weight errors. So in the past, we've had medical trained experts locate significant weight errors for accuracy and concluded that medical experts can in fact locate these weight errors of clinical significance. In other words, weight errors worth a clinician's time. Now I can sort of explain the features of the tool that we have made to support the development of the machine learning algorithm called the visual annotation tool. So for this visual annotation tool, we can choose a data point and modify the colors of that point to indicate whether or not it is an error. All data points are by default set to blue, in other words, not an error. So the first feature of the visual annotation tool is grid size, which enables users to see either 16 growth charts or 25. Then there's one-step versus two-step annotation. One step enables the user to immediately annotate the charts upon clicking on it. Two-step requires the user to click on all charts that might possibly have an error and annotating those charts after going through all growth charts. For one-step annotation, you would simply click on the graph and you immediately annotate the point if there's a potential error. For two-step annotation, you can select on multiple graphs and annotate the graphs later. So for the purpose of this study, we tested the usability of the visual annotation tool. On the left is the experimental workflow for this experiment. We first recruited participants, collected data, analyzed the data, which can be categorized into survey responses about the system, SUSU usability, and the system data, i.e. log data. For the participants, we divided the participants into certain groups to test the different settings of the system. So for each participant, this is how the data was collected. We started with the introduction of the project and the VAT. We then assigned login IDs for the participants. The participants would annotate the data. The participants would fill out a survey, and then we would interview them, and that's the end of the study for that participant. So once we obtained the data from all the participants, we collected their survey responses, which included both standard system usability questions and 6 additional other questions that our research team had designed. We also collected system data regarding what each participant did on the program as displayed in the chart, which is simply a sample of what they clicked on and the corresponding timestamp. We then calculated the SUS score and performed statistical analysis on the log data using primarily the timestamps and the correlated data with the VAT settings that the participants were assigned to. And for this study, the results displayed that the VAT has high usability with an average of 86.4 and a standard deviation of 6.8. The average for each participant is listed on the right. For the additional questions, the averages for each question also indicated to us that the system had high usability. In addition, according to the log data, it took less than 10 minutes on average to analyze 225 growth charts. In addition, the statistical analysis indicated that there was a significant decrease in time when the grid size was larger. However, most of the statistical analysis performed led to insignificant results, and we'll talk about that later. So overall, the VAT demonstrates high usability and efficiency. However, it also provides high flexibility of user interface, and I say this because of the largely insignificant results from the statistical analysis performed in the log data, as I stated in the previous slide. This indicates to us that there is no quote-unquote fixed setting of the visual annotation tool that works best for individuals besides the larger grid size. So therefore, we can provide several options to the users based on their preference to increase efficiency. In addition, from the design of this study, we recommend system usability to provide input and modifications for designing and improving systems. And the last point that I want to make is that visual analytics principles, are necessary for alleviating labor-intensive tasks. The limitations for this study include other possible methods to evaluate system usability and not testing the participants for accuracy, but rather usability. For future works, we will be utilizing the VAT to assist supervised algorithm development, utilizing larger data sets to collect a large amount of data analysis for the algorithm to make it as accurate as possible. In addition, our overarching goal is to develop the machine learning algorithm as a clinician decision support system. So a quick thank you to our collaborators. And if you have any questions, please feel free to reach out to the corresponding author, Dr. Danny Wu. Thank you.